In this part of the video, we're going to prove this Picard iteration actually converges to somewhere. So first we're going to choose any value x in between a and a plus beta and fix the value here. If you keep iterating this one for fixed value of x, and it turns out this number exists, it doesn't go to infinity or oscillates or anything. Let me remind you of probably the only technique you have learned in Calc 2 about proving convergence of a function. First of all, what we learned there is a series. When we're looking at the sequence here, you can write it as a sum of terms. So here it's a sum of functions, just like in the Taylor series. If you look at the Taylor series, this is actually Taylor polynomial. It's cutting in the nth power. You are keep adding this individual term over and over again. So we're looking at the functions as a sum of things. We're adding one more term of this type at a time. As you can see, as we add more and more, and if this converges, and then this becomes a Taylor polynomial, for many elementary functions, those functions can be written in terms of Taylor polynomial like this. So these are just like YNs we're looking at. We're not assuming YN, our convergent function or solution, is analytic or anything, but we're going to use this idea of writing YN as sum of functions like this. Here's one way to write this one term in terms of these Tn plus 1 and Tn. Suppose these are the function you get out of Picard iteration. How we're going to describe this individual term is actually subtracting these two adjacent index function. So if you write it out, this Tn plus 1, it's going from 0 to Tn plus 1. Tn will go 0 to n. So a lot of overlap from 0 to n will cancel out, just leaving the last term in here, which is bn plus 1 times x minus c raised to n plus first power. So if you subtract the polynomial, you get this one. So if these are the function you get out of Picard iteration, if you want to write this yn from Picard iteration as a sum of things, those individual terms look like this yn plus 1 minus yn, of course. So our goal is a ynx that is coming out of Picard iteration is written as a sum of functions like this, just like a Taylor series, but we're not assuming yn is a power series or anything. So here's the setup. Picard iteration clearly defines this yn, and y0 of course is still the constant function, and then we can define this individual function as the difference of these two adjacent functions. Once you write a function, we write a function like this as a sum of functions. Those techniques of proving convergence from calculus 2 or integral calculus is available to us. That's why we're doing it this way. Alright, the technique, the method from calculus, integral calculus I was talking about is this statement. Is absolute convergence implies the convergence here. This looks like, let me pull it down so that I can show the rest of the part. I'm going to show this much. Now yn, if you, for example, if you fix the value of x, then this becomes a finite series, and we want to see how it behaves as n approaches infinity, of course, and that's a series. Absolute convergence means if I change this individual term here into a positive term by putting absolute value, if that still converges, no matter what the sign was, it means it still converges. So we're going to establish the stronger statement, this absolute convergence of this series for fixed x value. Then it'll obviously prove the convergence, general convergence. So this is our goal. We change that term to a positive term and look at this series of a positive term and show this one converges. That'll imply that the original series converges as well. So by definition, here's gk, that's the difference of this yk and yk and k minus 1, and this is going to be rewritten using this Picard iteration. So a statement about this one is going to be stated in terms of k minus 1 and k minus 2 as we apply Picard iteration and the definition of, namely the definition of yk and yk minus 1. So here they are. The yk is under this recursive definition is this Picard iteration with k minus 1, this one here with k minus 2. When you cancel this y0 and y0, and notice that these two integrals are in the same range, a to x and a to x, you can bring them inside the single integral. And here it is again, the same function value, difference of a function value, t is the same, and yk minus 1 and yk minus 2 is the only difference, so that you can realize this difference of function value using mean value theorem, namely special values of a derivative and in the second slot, which is partial derivative with respect to y. So here's the partial. This whole thing is exactly equal to the special value of the partial, where yk minus 1 star is in between yk minus 1 and yk minus 2, and we multiply the difference of the input value, which is this one here. Well, if you think about what the gk was the difference of these two values, so this will be gk minus 1. So gk is now related with the gk minus 1. And it's part of our hypothesis that this f has a continuous partial, so this one will be always bounded by some value, like m2 or something. So it's bounded by some number m2 that uses that this t and yk minus 1 star is inside the box d bar, which has width beta and the height 2 times r, which was proved in 1 that if you do the Picard iteration, this point stays within the box, and this is where exactly we use this one, use that property. There are a couple other spots and later on we use that, but it is the importance here. Right, so if you look at this statement that this was exactly equal to each other, but now if you put the absolute value around it, then if you bring that absolute value inside the integral, then it gets bigger. So this one is going to be bounded by m2, and that one is now rewritten as a g sub k minus 1. So here it is. There's this nice m2, and this gk and gk minus 1 is a functions they're related like this. Now from here we'll recursively unfold these two things and get a nice statement. So I copy the statement over here. This is kth term of y expansion, and this is k minus first term. We're going to start from g1, and from there we calculate g2 and just inductively claim that how the gk looks like. Because of this relation, g1 is less than or equal to m2 times this integral with the g0. If you think about the g0, that's the very first term in the series, so that must be the constant y0 here. So that's a constant, so integral of this one is simply y0 times x minus a, while x is varying still in that box. So we have g1 is bounded by this function, so we're going to use this one to calculate the upper bound of g2. So that recursive relation gives you g2 less than or equal to m2 times integral of g1. Then we're going to replace that g1, absolute value of g1, by this upper bound and get a very specific upper bound, which is this one. This g1 is replaced by m2y0, not x minus a, t minus a, because that's our integral variable. Then it gives us m2, there are two m2s, and y0. Actually, this y0 is supposed to be absolute value. It's typo. We must have absolute value everywhere around this y0. Sorry about that, because we put absolute value everywhere. But this part's okay, x minus a, assuming x is greater than a. So that's a specific upper bound for g2. So g2 is growing like this, a lot like a Taylor series. It's not exactly the Taylor series, but we're making a comparison with the g2 with this Taylor like terms. This is only 2 terms, but I encourage you to do 3rd and 4th term to convince yourself that kth term always bounded by the following. This m2, this 2 is exactly this index, m to the kth power, absolute value of y0, not at y0. And as you integrate more and more, if you think about this one, that just picks up usual antiderivative of x minus a, so that picks up k factorial and the kth power here. So the kth function, kth term of yn there is going to look like this. Now let's finish up the proof of absolute convergence. The yn here is the function we're looking at, and it is actually less than or equal to absolute value of this individual term, and because it's a positive, proving that this is bounded by something will prove that this one exists, this absolute value. It's called monotone convergence theorem. As we add more and more terms, because these are positive, it's going to increase. If it is absolutely bounded by something that doesn't depend on n, it means it cannot exceed that term. Therefore, it proves that it must converge to something. So let's replace the gk with this upper bound here, which is this one. Again, this absolute value of y0 is the correct one. So k factorial, you can put this m2 kth power and x minus a kth power together like this. If you think about it as k factorial and the power of something, this is exactly the series expansion of the values of the exponential functions. Again, with the correct term, absolute value y0, this would be correct. This value is exactly equal to e to the m2 times x minus a in there. If you look at the Taylor series of e to the x and put this thing in there, you will get exactly this part. So we prove that this the series of positive terms is bounded by that, therefore it converges. So the absolutely converges means actually yn is also converging. This was true for any given x value x. Then as you increase this n, this value exists. So this creates actually function. If you choose any value x there, and if you send n to infinity, this becomes a number exists. So given x value, we have this value assigned to it. So this is a new function. In the next part, I'm going to show that this function is actually continuous.